Hey guys, here are your 4.3 day 2 notes on the real zeros of a polynomial function. In today's notes, our main goal is going to be to find the real zeros of a polynomial function. We want to find and calculate the zeros, right? The problem is when the degree of these polynomials get higher and higher and higher, like degree 4s, degree 5s, degree 6s, to set those polynomials equal to 0 and solve for the zeros, it becomes harder and harder. So the rational zeros theorem, otherwise known as your P's and Q's, if you remember from Algebra 2, the rational zeros theorems helps us break down these higher degree polynomial functions that are harder to factor. All right, but I don't want you guys to forget that you are going to still be using your common factoring techniques. So don't forget about GCFs and difference of two perfect squares and your factor by grouping. That usually happened when there were 4 terms and you would group the first 2 and group the second 2 and whatnot. All right, don't forget that sometimes you have even degree polynomials that aren't quadratics, but they factor like a quadratic. So even degree meaning like your degree 4s and your degree 6s and your degree 8s, right? Here's an example of a degree 4 polynomial. So it's not a quadratic, but it factored like 1. Instead of needing x and x, I needed an x squared and an x squared to get me my x to the 4th. And then what adds to the 6x squareds and multiplies to the 8? A 4 and a 2, right? And then your rainbows will get you your 6x squared. So it's not a quadratic, but it factored like 1. So don't forget, these are still going to pop up as ways we can find the zeros. And if we can use these techniques, trust me, we would rather use these techniques than have to go to our P's and Q's. But when all else fails, if you can't factor it like this, these higher degree polynomials, then your last resort is going to be using your P's and Q's, your rational zero theorem, or the graphing calculator. Sometimes it's going to come down to that maybe it's too difficult for us to solve by hand algebraically, and we're just going to have to depend on that graphing calculator to give us some clues. Okay? All right, so you should remember the rational zeros theorem. Your book last year might have called it the rational root theorem, but it's the same thing. My students always remembered it as your P's and Q's, okay? So the rational zeros theorem, again, it's just going to help us break down these higher degree polynomials so we can find their zeros. The rational zeros theorem says, let f, Zach, you have to stop that, bud. It's too loud with the sirens. Let f be a polynomial function of degree 1 or higher of the form this. So again, it's just a polynomial function in descending order from highest degree all the way down to the constant a sub 0. All right, where each coefficient is an integer. If p over q in lowest terms is a rational zero of f, then p must be a factor of a sub 0, the constant, and q must be a factor of a sub n, the leading coefficient, okay? So the rational zeros theorem is saying that if p over q is a 0 to this polynomial, it's only because p must have been a factor of, what does it say? A sub 0, the constant, and q must have been a factor of a sub n. All right. So guys, I don't know if you realize it, but when we are factoring quadratics, which are technically the easiest ones to factor, you're already getting p over q as your solutions, as your zeros. All right. If you think about how we would factor this quadratic, right? Whatever we put here and here, they have to be factors of 2x squared, which is our a sub n, if you will, right? So we're putting factors of a sub n and a sub n there, which are going to be our q's, right? Q must be a factor of a sub n. So you're putting a q here with an x and a q here with an x, right? To get that x squared there. All right, and then whatever number you put here and whatever number you put here, they have to be factors of -3, which is your a sub 0, if you will. So you're putting a factor of a sub 0 here and here, which are your p's. P's must be a factor of a sub 0. So guys, when you set these factors equal to 0 and solve, if I took qx plus p and set that factor equal to 0, I would minus p and I would divide by q. And your 0 is some version of a p over a q. So we're already getting p's over q's as our zeros when we solve quadratics, okay? And that's what the rational zero theorem is saying. If you are a real zero, p over q, then p must have been a factor of the constant and q must have been a factor of the leading coefficient, all right? That's what the rational zero theorem is saying. So we can use that to come up with a list of possible zeros that could be zeros to given polynomials, all right? All right, so let's look at example example 1. I know if you guys remember from Algebra 2, this is usually a process you guys did not like because it kind of takes a while. We're going to try and trim that down by kind of imploring the graphing calculator to take a little bit of the guesswork out, all right? But here we go. So it says, list the potential rational zeros of f of x. So guys, here's a degree 3 polynomial that has 1, 2, 3, 4 terms in it. Well, I don't know about you, but if I was trying to find its zeros and set it equal to 0 and solve, I right away would have tried factor by grouping. I would have grouped the first two, grouped the second two, see if I got that common term. But I'm telling you right now, if you tried to factor this by grouping, it wouldn't work. All right, so you'd be stuck. How else are we going to break this down, this degree 3 polynomial, and start to factor it or break it down to find its zeros if it doesn't factor by grouping, right? And there's no GCF, what are we supposed to do? Well, the rational zeros theorem is going to help us come up with a list of possible zeros. And if I can use that list of possible zeros, I can start seeing which ones divide evenly in and get me that remainder of 0, right? And then I can start breaking that degree 3 polynomial down into a degree 2 polynomial and whatnot. And if we can get to a degree 2, that's great. If we can get to a degree 2 polynomial, we can factor it, or at worst, use the quadratic formula. All right, so here we go. So if it's going to have any rational zeros, right, then they are going to be our p's over q's. Now, a lot of times students forget who's p and who's q. So I always forget, my teacher always said, p is your factors of the constant, and Q is your factors of the leading coefficient. So I always remembered it, instead of P over Q, I always remember F con over F co, factors of the constant over factors of the leading coefficient. All right, so factors of the constant. The constant is 6. So what are factors of 6? 1, 2, 3, and 6, right? And then factors of the leading coefficient. Who's the leading coefficient? 2. So what are factors of 2? 1 and 2. Now, it doesn't matter what order you list them in. I have a little bit of OCD, and sometimes I like to list them in least to greatest, but it doesn't matter. Okay, so now we're going to start compiling a list of possible zeros using these factors, okay? Now, we don't know if the zeros are meant to be positive or negative, so we're going to make a plus or minus version of all of these. So we're going to say a possible 0 is plus or minus. Take the top and start putting it over all the bottoms. So 1 over 1 is 1. So positive 1 or negative 1 is a potential real 0 to this polynomial. All right, take 1, put it over the next denominator, 2. So plus or minus 1/2. So positive 1/2 or negative 1/2 is a potential 0. All right, I've done that one. So now let's go to the next numerator and put him over the two denominators. Now, you don't have to list repeats. All right, so it's going to be plus or minus 2 over 1 is 2. And then plus or minus 2 over 2 is 1, and I've already listed it, so I'm not going to list it again. I'm going to go to the next numerator and start matching it with denominators. So plus or minus 3 over 1 is 3. Plus or minus 3 over 2 is 3/2. And then plus or minus, go to your next numerator, 6 over 1 is 6. And then plus or minus 6 over 2 is 3. And I've already listed plus or minus 3, so I'm good. So guys, if there's going to be any real zeros to this degree 3 polynomial, now again, he can only have 3 zeros. If he's going to have any rational zeros, they are going to be a number on this list. Okay. All right. So that's all it said. It just says list the potential zeros. These are all the potential real rational zeros of this polynomial function. These are all potential crossover x-axis points. Okay. So example 2 says, all right, well, now I want you to actually find the zeros of f of x in example 1. So I have my list of potential. So I don't know if you guys remember, what you're supposed to do now is, in any order that you want, take them and start testing them synthetically to see who gets you the remainder of 0. Once you know who gets you a remainder of 0, you know that one divided evenly in, and you can start breaking this degree 3 polynomial down to a degree 2 polynomial using that synthetic division. So I don't know if you guys remember, but testing all of these numbers was really, really annoying. So what we're going to do, I'm going to cheat. I'm going to go to the graphing calculator, and I'm going to see where this crosses over the x-axis at, close to which one of these numbers, so I know which one's a better one to start testing, so I don't waste too much time. So I've already typed in all of the examples from today's notes. So here's the first graph. It's the only one I have turned on. So if I hit graph, here's his graph. All right, so it looks like it's crossing somewhere between 0 and -1. But remember, in between there, it might not be a nice fraction. It might be an irrational number, like the square root of, 2 2, even though it would be more over here, negative 1.4. But if it's irrational, that could still show up as a decimal. We don't want them. They won't be on this list. All right. It definitely looks like it's crossing at positive 1. So I'm going to try positive 1 as a first number to use. All right. So if I use positive 1 as my magic synthetic number, right, as my potential 0, let me go get my coefficient so I can do my synthetic. Remember, synthetic, you have to look for missing terms. So I have an x cubed, an x squared, adjust x, and adjust number. So I'm not missing any terms, so I won't be needing to fill in any zeros as my coefficients. So I need 2, 11, negative 7, and negative 6. All right. Bring down the first coefficient, and we begin the synthetic process. All right. Now, again, you could plug 1 into this polynomial to see if a 0 comes out. That would also be telling you if it's a factor. The problem is once you get 0, you're going to have to do this to start getting the coefficients to the next easier polynomial to work with. So I just always go right to the synthetic. All right. So if I do my multiply and adding process, I'm hoping for a remainder of 0. All right. 2 times 1 is 2. 11 plus 2 is 13. 13 times 1 is 13. Negative 7 plus 13 is 6. 6 times 1 is 6. I add, I get 0. So that's my remainder. So that means 1 is a 0 of this polynomial. It means it could be written as one of his factors. So right now I know one of the zeros is x equals 1. I know he's a 0, so hang on to him. He's one of my 3. So now, after I've done one round of synthetic division, this degree 3 polynomial has turned into a degree 2. So these are the coefficients to a degree 2 polynomial. So if I look at it, 2x squared plus 13x plus 6. All right, if I want, I can just set this quadratic equal to 0, and I can try and find my remaining 2 zeros by working with this quadratic. Now, by all means, you could take these coefficients and start working with another 0 or potential 0. You could come back to your graphing calculator and see another number that you think it crossed at. All right, but once I get to a quadratic, I don't see any need, because you could be wasting time in the sense that the next 2 zeros are going to be irrational or imaginary. So I want to make sure that I just get to my quadratic and then I can work from there. So I'm going to see if this factors. It does not have a GCF. All right, so what times what gets me 2x squared, 2x, and 1x. Whatever I put here has to multiply to 6, and then my rainbows better add up to 13. So I could do what, 2 and 3 or 6 and 1? Well, if I put a 6 here and a 1 there, I'll get 1x and 12x plus. That looks good. All right, so now set these factors equal to 0, and you get your remaining 2 zeros to this degree 3 polynomial. So I'm going to get what? X equals negative 1/2. And x equals negative 6, and I already had x equals 1. And there are my 3 real zeros to this degree 3 polynomial function. Okay, now on your homework, I'm pretty sure they're going to ask you in the last step, once you have found the zeros, they're going to ask you to write your polynomial in factored form. So a lot of times they ask you to write it as your real zeros as linear factors. So guys, there's 2 things you could do. You have 2 factors here, right? 2x plus 1 and x plus 6. So you could say 2x plus 1, x plus 6. If 1 was a 0, then he must have been a factor of x minus 1, so that when you set x minus 1 equal to 0 and solve, you get positive 1 as your answer. All right, and those could be your factored form of the polynomial function f of x. Now just make sure that your fronts multiply out to the leading power function. 2x times x gets me a 2x to the third, so it matches. All right, now another thing your book allows you to do, when you go to write the factors in factored form, you could say f of x equals, you are allowed to take each one of these zeros and write them as linear factors like this. So if x equaled negative 1/2, then you could say x plus 1/2 was a factor potentially. Even though we usually don't see it like that, you are allowed to write it like that. And then x equals negative 6, you could say is x plus 6. And then x equals 1 would be your x minus 1. The problem is now your fronts only multiply out to a 1x cubed, and I need them to multiply out to a 2x cubed. So all you'd have to do is stick a 2 out as a leading coefficient, and now 2 times x times x times x would get you a 2x to the third. So you are allowed to write it like that as well, okay? All right, perfect. All right, let's try the next one. All right, the next one says, list the potential rational zeros of f of x equals 3x to the third plus 8x cubed minus 9x plus 2. Well, guys, just out of habit, seeing these four terms, before I would try my p's and q's, I would look to see if it factors by grouping. But it doesn't. I don't get that matching factor, so I don't have to do that in the sense that it's not going to work anyway. So I am going to use my P's and Q's. All right, so it's just asking me to list the potential. It's not asking me to find them yet. So let's do our P's and Q's. What are the potential rational zeros? So P over Q, or F con over F co. Factors of the constant over factors of the leading coefficient. So factors of the constant are, well, factors of 2. Well, that's nice because it's just 1 and 2. All right, and then factors of that leading coefficient. The leading coefficient is 3, so the only factors of 3 are 1 and 3. So it's awesome when you don't have a lot of factors because you're not going to have a very long list of potential zeros. All right, so here we go. Let's start making our list. So the potential zeros could be plus or minus 1 over 1 is 1, plus or minus 1 over 3 is 1/3, plus or minus 2 over 1 is 2, plus or minus 2 over 3 is 2/3. So again, if this polynomial is going to have a rational zero, one or all three of them, they are numbers on this list for sure. They have to be, okay? All right, so that's that example. Let's go to example 4. So example 4 says, let's have to continue this, sorry. All right, example 4 says find the zeros of f of x in example 3. So now we're going to try to find its zeros using the potential ones that we found. So again, this was the annoying part where you kind of had to just start picking a number and going for it. We're going to use the graphing calculator to get a better idea as to which one I want to go with. All right, so let me just go back to y equals. I'm going to turn this one off. Go to the next example that I already typed in. I'm turning it on. Let me go to its graph. So this one looks like it is crossing somewhere in between -3 and -4. Again, that could be a fraction, but it could also be irrational, which means it wouldn't be on this list if it's irrational. And then it looks like it's crossing in between 0 and 1. So on my list, I have 1/3 and I have 2/3 in there, right? And I don't want the negative version, I want the positive version. So I'm going to try 1/3 first and see how it goes, okay? So if I try 1/3 first to start breaking this polynomial down. All right, well, let's get my coefficients. Degree 3, degree 2, degree 1, just number. I'm not missing any terms. I don't need to fill any zeros. It's going to be 3, 8, -9, and 2. 3, 8, -9, and 2. Okay, so again, if you are going to use a fraction, a lot of people don't like testing them. If it's going to be a fraction that works, it's going to work out pretty nicely all the way through. All right, so we're hoping for a remainder of 0. So let's bring down 3 and let's start on multiplying and adding. 3 times 1/3 is 1. We add it, we get 9. 9 times 1/3 is 3. We add it, we get -6. -6 times 1/3 is -2, and there it is. I get a remainder of 0. So now this degree 3 polynomial function, after one round of synthetic, I now have the coefficients to a degree 2 polynomial function. And I'm telling you, if I can get myself to a degree 2, I'm good to go. Now, it did look like it bounced at that 1/3. So if you wanted to use 1/3 again, if it's a double root, it'll work in another round of synthetic, okay? So now I know x equals 1/3 is a root, right? And it definitely looked like it bounced. So let's do it again. Let's try it again. So if I try it again, I could avoid having to factor or use the quadratic formula if it doesn't factor. All right, so I'm going to get you know what? I think I'd rather show you the factoring just for the homework problems. I'd rather go to the one because I think it's a quadratic formula and I'll feel better if I show you one. All right, so I am going to use these as my coefficients to a degree 2. So now I'm going to have 3x squared plus 9x minus 6, only because it may not be bouncing. It could be crossing, and I'm not technically seeing it right, not zoomed in yet. So let's go from here. All right, set this quadratic equal to 0, and we'll solve. I'm going to divide out the 3 to make it easier numbers to work with. Okay. All right. So if we do that, it looks like it's not going to factor because nothing's going to multiply to -2 that adds up to 3. So I am going to have to use the quadratic formula to get my remaining 2 zeros, which means they definitely would not have been on this list because they're most likely irrational and potentially they could be imaginary. All right. Because we can get imaginary zeros when we use the quadratic formula. All right. So let's see. X will equal negative the opposite of B. It's going to be 9 plus 8 is 17 over 2. So yes, the square root of 17 does not simplify. So this is going to stay as an irrational 0. So technically, one 0 is -3 plus root 17 over 2, and the other 0 is -3 minus root 17 over 2. So that would be, and then don't forget x equals 1/3. And those are your 1, 2, 3 real zeros to the degree 3 polynomial function we were working with in this example. Okay. All right. So again, I think what's going to happen at the end of this problem on your homework, they're going to ask you to write this in factored form. So just because I don't have a lot of room, I want to remind you, these are our zeros. So to write them as factors, watch how weird this is going to be. All right. X equals 1/3. You guys could write as x minus 1/3 as a factor. All right. Again, you could change it back into 3x minus 1 because that would get you the 1/3, but you're allowed to leave it like this. And then as weird as this is, we're going to say it's x minus, and then in parentheses, you're going to put -3. Usually I always start with my weird ones with a minus because technically if I was just going to add this whole thing over, it would stay with the -3 if I set them equal to 0. Okay, so that's a factor, believe it or not. And then x minus, and then -3 minus root 17 over 2. All right, I'm just going to clean this up. So now I get x minus 1/3 times x. If I just root my negative, that's going to be plus 3 minus root 17 over 2. And then it'll be x plus 3 and then plus root 17 over 2. And now if you look, your fonts, x times x times x, it doesn't multiply out to the original 3x to the third, that leading power function that we were trying to model. So all you got to do is stick a 3 in front if you want it to multiply back out to that 3x to the third. All right. If you had written this factor as 3x minus 1, then you wouldn't need the 3 in front. Okay. But you are allowed to write it just like this, as weird as that would seem. Okay. And now you've written it in factored form. Now, technically, you could have written it as x minus 1/3, and you could have used this quadratic factor, but a lot of times they specifically say to write them as linear factors. It's only the imaginary ones they let you leave as quadratic factors. Okay? All right. All right, perfect. So let's go to the next example. Okay? All right, so this one says list the potential zeros of the polynomial function f of x equals this. So now we have a degree 4 polynomial. All right, again, you could try to do factor by grouping, but it doesn't look like you're going to get that matching term. So I'm not going to even try it. I'm going to go right to my P's and Q's and try and get some potential zeros to break this degree 4 polynomial down. Now, hear me out. If this is a degree 4 polynomial, one round of synthetic is only going to get you to a degree 3 polynomial. Maybe that degree 3 polynomial will factor by grouping. If not, we're going to have to try and get that degree 3 polynomial down to a degree 2 polynomial using more of those potential zeros and another round of synthetic. All right, so the higher the degree, the more and more complicated this process is going to get. All right, so again, let's get our P's and Q's. What are our potentials? So P over Q are F con over our F factors of the constant over factors of the leading coefficient. So factors of 4 are 1, 2, 2, but we don't list repeats, so 1, 2, and 4 over factors of the leading coefficient, 3, which is just 1 and 3. Okay, so now we're going to get plus or minus 1 over 1, plus or minus 1/3, plus or minus 2, plus or minus 2/3, plus or minus 4, plus or minus 4/3. So if this degree 4 polynomial function has any potential real zeros, they are somewhere on this list, okay? All right, so now example 6, they want us to actually go ahead and find the zeros of this polynomial function. So we'd have to start picking numbers off this list and start testing them synthetically. I'm going to use my graphing calculator as a cheat. All right, if I go to my graphing calculator, all right, let me go to the next example. I have to turn this one off, turn on this one. Let me see its graph. All right, there we go. And it looks like on this list, we have, oops, if you can see, it looks like -2, maybe even -1. All right, it looks like it could be bouncing at -2, but again, it's hard when it's not to tell when it's not zoomed in like that. So I'm going to try -2. All right, let me get my coefficients. I have a degree 4, degree 3, degree 2. I have no x's, so I'm going to have to fill in a 0 as a coefficient for the x's and then -4. So do not forget to fill that 0 in when you're doing your synthetic. All right, so I need 3, 13, 15. Then I got to fill in a 0 and then a -4. All right, let's bring down the 3 and let's hope for a remainder of 0. Okay, so 3 times -2, 6. And it worked. So that means x equals -2 is definitely one of our zeros. It got us a remainder of 0. It's definitely a factor. It's definitely a 0. All right, now these become the coefficients after one round of synthetic from a degree 4. These are now the coefficients to a degree 3. So this would be 3x to the third, 7x squared, 1x minus 2. If I tried to look to see if grouping would work, it's not going to. So I'm going to just go right into taking these new coefficients and going right into another round of synthetic. So again, because it looked like -2 bounced, I'm going to try it again. If it's a double root, it'll work in a second round of synthetic. If it has a multiplicity of 2, it'll work 2 times in your synthetic process. So I'm going to try -2 again. All right, take my new coefficients, 3, 7, 1, -2. Let's see if I can get another remainder of 0 out of this. So I bring down 3, multiplying and adding. And yep, I did. I got another remainder of 0. So that means that -2 is another 0. So right now, out of the 4 zeros we're looking for, I know that -2 is 2 of them because the multiplicities each count as 1 0. All right, so I know -2 is a double root. Now I need 2 more. Well, guys, after 2 rounds of synthetic, this degree 4 became a degree 3 and now a degree 2. So these are the coefficients to a degree 2 polynomial. So that's going to be 3x squared plus x minus 1 equals 0. So now I'm just going to see if I can factor my quadratic or use the quadratic formula, okay? All right, it doesn't look like it's going to factor. I don't think 3x and x and then anything that multiplies to 1 will get me 1x in the middle. So I'm going to go right to my quadratic formula. It's going to be 1 plus 12 is 13 over 6. So you're going to get -1 plus root 13 over 6 as one of your zeros and -1 minus root 13 over 6 over your fourth zero. So I have 1, 2, 3 and 4 right here. So don't forget x equals -2 and x equals -2. And those are your 4 zeros, all right, to your degree 4 polynomial. 2 of them were real and rational, and then 2 of them were real and irrational, right? Really ugly decimals, okay? All right, so again, they're going to ask you to write this in factored form. So these are going to be really easy to write as factors. This one is going to be really, really weird to write as factors, okay? Now again, technically you could write this as one of your factors and then an x plus 2 and an x plus 2. The problem is this is not a linear factor, it's a quadratic factor, and sometimes they specifically ask you to write your zeros as linear factors, okay? So really, really quick, if I just show you that, all right, we have zeros, -2, -2, and then these two. So to write him as a factor, that's just going to be x plus 2. To write him as a factor, that's going to be x plus 2. And then this one's going to be x minus, and then in parentheses, -1 plus root 13 all over 6. And then x minus, in parentheses, -1, oops, and then minus root 13 over 6. Okay, I'm just going to distribute my negative. I'm going to get x plus 2, x plus 2, and then it'll be x plus 1, and then minus root 13 over 6, and then x plus 1, and then plus root 13 over 6. And now again, your fronts, x times x times x times x, they only multiply to 1x to the 4th, and our leading power function in this problem was 3x to the 4th. So that could just be as simple as popping a 3 in front, all right? And you could call it a day, and you would have the correct polynomial function in factored form, okay? All right, perfect. I think there's one more problem on the notes. Yep. All right. And this one just says go right to finding the zero. So it doesn't have you finding the potential ones first. It just has you going right into finding the zeros. So guys, this is crazy. All right. It's a degree 6, so it potentially has 6 real zeros. All right. Let's make our list of P's and Q's, our possible rational zeros. So factors of the constant over factors of the leading coefficient, FCon over FCO. So I need factors of 84, which is a laundry list, let me tell you. All right, so we would have 1 and 84, 2 and 42. Sorry, don't mind me the way I write them, it's just my OCD. 3 and 28. All right, 4 and 21. Then we would jump to 6 and 14, I believe. And then we would jump to 7 and 12, and I believe those are our last factors, all right? So those are factors of 84 over factors of the leading coefficient, which thank God is 1, and the factors are 1 and 1, but we don't list repeats, so it's 1. So technically, all the potential zeros are positive, negative, all of these whole numbers when you put them over 1. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, and so on. All right, you could go to the graphing calculator and look just to save a little bit more time. I'm going to tell you right now, I already did that, and it looked like -2 was a potential. So I'm going to try -2 right off the bat. All right, let me get my coefficients. I have a degree 6, degree 5, degree 3. So I'm missing a degree 4. So I'm going to have to fill in a 0 for my missing degree 4 term. All right, degree 3, degree 2, degree 1, and then my constant. So I'm going to have to fill in 1 0. All right, so I'm going to get 1, 4, 0, -16, -37, -84, -84, and we're shooting hopefully for a remainder of 0 at the end. All right, so bring down the 1 and let's do this, guys. We're going. We're going to do 1 times -2 is -2. 2, -4, -4. It's going to be 8. It's going to be -8. It's going to be 16. It's going to be -21. -21 times 2 is positive 42. add them together. We're going to get negative 42 times a negative is positive 84. 0. There it is. So now this degree 6 polynomial, after one round of synthetic, has now turned into the coefficients to a degree 5 polynomial. So again, it's not really getting us much anywhere. It's not like I'm going to be able to factor this degree 5 polynomial with these wild coefficients. So I'm going to keep going. You could go back to your list of potentials and try another one. But again, sometimes the higher the degree, the more potential you have for the multiplicities, for the double roots. So I'm going to try -2 again with my new coefficients to see if it's another 0. So right now we know we worked one time. So let's hold on to -2 as 1, 0. Let's try it again. All right, use your new coefficients. Let's see if we can get another remainder of 0. And we did. We got another remainder of 0. So now this degree 6 polynomial became a degree 5 polynomial after one round of synthetic, and now it's a degree 4 polynomial after a second round of synthetic, and we now know x equals -2 is another 0. So we have 2 zeros out of the 6 that we're looking for. So guys, look, this is a degree 4. There's no degree 3, that's a degree 2, there's no just x, and then that's your just number. So this potentially could be a degree 4 that acts like a quadratic with all these missing terms in between. So let me see it. This is going to be 1x to the 4th minus 4x squared, and then minus 21. So guys, that looks like a degree 4 that might factor like a quadratic. So to save myself some more potential rounds of synthetic, I'm going to see if I can factor this degree 4 and start breaking it down. All right, so it looks like, how would this factor? What and what multiply to x to the 4th and allow me to get x squareds in the middle? An x squared and an x squared. What multiplies to -21 and then adds up to -4x squareds? -7 and +3, right? -7x squared, +3x squared. It totally factors. So now just set these factors equal to 0 to find your remaining zeros. We already have 2 out of our 6. Let's get this one. So if I set x squared minus 7 equal to 0, I get x squared equals 7. Use my square roots. X equals plus or minus root 7. So now I have 1, 2, 3, 4 out of my 6. All right, and then if I set x squared plus 3 equal to 0, I'm going to get x squared equals -3, take the square root, and I'm going to get x equals plus or minus I root 3, which means 2 out of the 6 real zeros are actually, out of the potential zeros are imaginary, and they're only asking you to find the real zeros. So we don't need the imaginary ones right now because the imaginaries don't turn into x-intercepts. So right now, this degree 6 polynomial, out of its 6 zeros, only 4 of them are real. The remaining 2 are imaginary. Are you okay?
Yeah, why don't you can be done?
2 more minutes, okay? All right, so technically, when you're listing your answers, you're only going to list your real ones in the My Math Lab as your answers. You don't list the imaginaries when they've clearly only asked you for the real ones. All right, now if they ask you to write it in factored form, if you write it in factored form, let me just sneak over here real quick. All right, we have zeros, x equals -2, x equals -2, and we have x equals positive root 7 and x equals negative root 7. And then you had the plus or minus I root 3. So what you do with your imaginary, just leave it as the quadratic factor it already was. So we're just going to leave that as x squared plus 3, okay? All right, so if I write him as a factor, that would be x plus 2, x plus 2. This would be x minus root 7, and then this one would be x plus root 7. All right, and then your x squared plus 3 comes down. And then they would multiply out x squared is going to be what? 2, 3, 4, 5, 6. So it multiplies to a degree 6, but I need a leading coefficient of 1. So we're good. So you don't have to stick any number out in front. All of these fronts will multiply out to the 1x to the 6th, that leading power function that we need it to. So this is what it would look like if you wrote it in factored form, okay? All right. All right, guys, I know that was a lot. And as always, please reach out to me if you have any questions. Just be careful with your P's and Q's and take your time and let the graphing calculator guide you as to which ones would be worth testing first, okay? Good luck, and let me know if you need any help.